Hello students, Mr. Rising here once again, and I want to talk a little bit today about bivariate data and making lines of best fit or linear best fit models. So when you get a bunch of data, right, and we need to make a prediction about what's the relationship in the data and where do we think the data is going or what might happen, it's amazing how powerful your brain is, because you will make a pattern. You will see something there. It takes a lot of calculation to do mathematically, but your brain is already like, wait a minute, I can connect the dots. Before we dive in, I want to just put out a vocabulary term, and it's called clustering. And when we work with data, bivariate data means it has two components, an X component and a Y component. You can think of it as an independent component and a dependent component. So time is often independent. How far something grew might be the dependent version. Anyway, the vocabulary term is clustering, and it's when data points in a scatter plot are grouped more in one part of the graph than the other. And you can see examples of clustering here. So basically in this example, we're talking about a study conducted to measure the effect of fatigue on typing accuracy. So basically over a 40-minute period of time, how accurate were people? And of course, 5 minutes into it, you can see the data is all clustered at this 5-minute mark, right? And the 10-minute mark and the 15-minute mark and so on. You're going to be doing some data work as well, and you're going to notice there might be some clustering of your data as well. So the clustering occurs when the data, there's a bunch of data points together. Now, we've already talked about outliers. An outlier is a point of data that just doesn't really fit anywhere with the rest of the data. It just doesn't seem like it's working very well. Maybe this person after 25 minutes got a phone call, or they were multitasking, or they were trying to eat a Twinkie and they were trying to type at the same time, and it just made a mess. Okay? So that's what clustering is, and that's what outliers are. So when it says describe the pattern, you can see this pattern does not appear to be a line. Like if I wanted to connect the dots, this definitely looks more like a curve than a line. I mean, I could draw a line right here, but I'm not sure a line would really be the best fit. I mean, look at that. It leaves a lot of error, and that's really not the point. So let me just put a little blue line there. Like that blue line, that doesn't look very good. You know what I mean? Let's just get rid of that blue line. Identify any clustering. There appears to be clustering, right? At every 5-minute mark, there definitely seems to be more clustering. Now at the 25, there's an outlier. After 15 minutes, notice how the data spreads out after 15 minutes. So right between 10 and 15, right, the data's really close together. It's clustered together. But as you move further away from it, the data points get wider and wider apart. And you can see the data is getting less clustered. And then identify any possible outliers. Yeah, another possible outlier would be at the 40-minute mark. Right up here, 90% accuracy at 40 minutes. Okay, great, but that doesn't really seem to fit the pattern of data. Of course, with everything going on in the world right now, the coronavirus and the number of cases, new cases announced every day, you can also see this is not what you would consider a linear relationship. I mean, it's definitely a curve. It seems to be going up very quickly. And this would be an example of an exponential relationship. So I can connect all the tops of these bars. Really, they are data points. Each bar is a day, it has a date, and then the number of new cases is the y-axis, right? So it doesn't have to be a bar graph. I can have a bunch of little dots here. But if I was going to connect them, I would connect them with a curve, and it definitely appears to be much more exponential. Now, when we are looking at scatter plots, and we are trying to make a line of best fit, what we've done before is after we plot all our points on the scatter plot, we then take a ruler and connect everything, as many of the points as we can on a single line. When you want to compare these two, and you look at graph A and you look at the little red line connecting all the points, and you look at graph B, you would say, well, graph A is a better fit. It hits more of the data points. It's in the middle of more of the data points. So like, even though right here I'm not touching any data points, I'm definitely in the middle of them. When I compare that to graph B, it's like, oh, I've got a lot of points over here that I'm I'm shooting below. I'm basically under-predicting what the real value would be. So in this example, I would say A would be a better fit because it's in the middle of more data points. There's less error between the actual data points, which are the circles, and the predicted values, which would be on the line. Now, when you get to algebra or statistics in high school, you'll learn more about what's called a least squares line of fit, and that's a mathematical calculation of what the best line, so rather than just eyeballing it, mathematically calculating the best line. In fact, we're going to do a little bit of this as well, but I'm not going to get into the calculation. We're going to let the computer do the work for us. You'll recall, just to go back when we talked about scatter plots and correlation, that this little letter R is called the correlation coefficient, and it is a number between and including -1 and +1. And a correlation of +1 means it's perfectly positively correlated, and a correlation value of -1 is perfectly negatively correlated. And what that means is when it's perfectly positive, for every increase you increase on the independent variable, you get an equal increase in the dependent variable, and so on forever. When I want to know how well a model works, I'm just introducing this idea. I'm not expecting you to calculate it. Well, you're going to calculate it, but I'm not expecting you to know the formula behind it. How well the line fits the data is called R squared. So you take this previous number, R, this correlation coefficient, and you square it. You multiply it by itself. And so if it was a -1, and you wanted to square -1, -1 times -1 is +1. And you would say that line, all the data points fit perfectly on the line, 100% of those values. So I just want to introduce this idea to you right now. Yeah, I'm getting rings over here on the side. One last thing I want to do here, and we'll wrap up the video, is let's work a real example. And we're going to answer about 5 questions and kind of go through it. So I have a scatter plot, or I have some data. And this is the relationship between study time and trying to predict a semester grade. And so basically, as you look at this, first of all, I want to say, well, what's the correlation? This is definitely a positive correlation, and it looks like a pretty high positive correlation. So I'm thinking this in the back of my head. All right, now number 1, imagine a line that best fits through the scattered points. What are 2 points that it would go through? Well, first of all, let's draw our line. And when I'm drawing my line, I'm thinking, well, can I go from 40? Let's go from 40. You know, that looks pretty symmetrical. I mean, it might go a little more like this. I'm going to go and I'm going to extend it beyond, right? I'm going to go like that. Bam. So I've got a line, and let me make it, well, again, we'll make it blue so it stands out a little better. Okay, now it says, what are 2 points that would go through? Well, to answer that question, look at the line, and let's just write our answers. Okay, we're going to go here. We're going to go number 1. Well, 2 points that it would go through. When I look at this, well, it definitely hits this first point. What are the coordinates of this point? Well, the x-coordinate is 0, 0 study hours, and my grade, 40%. Okay, what's another point that would go through? Hold on, let me pause my video. Okay, trouble avoided. Another data point on this line. It looks like, you know what, right here. I'm touching any one of these points, these red points that I'm touching. I would say I'm pretty darn close. So this looks like 3 hours. So let's go 3 comma, and then I'm between 60 and 70. So we're going to call that 65%. Question 2. What is your equation of your line of best fit? Okay, the form of a line is y equals mx plus b. So y equals m. What's the slope? So what I need to do here is I need to calculate the slope of my line. Well, since all these units are 1 over up over up. Oh, wait a minute. Rise over run. So I'm basically going, for every 1 unit I go over, from here to here, let's see, I went up 10 points over 1 hour. 10 points over 1 hour. 10 points over 1 hour. 10. It's not quite, it's a little bit less than 10. Let me get 2 points. Hey, let's just do it this way. Let's let's go back here and do the slope. M equals, and I'm going to do vertical. So let's do 65 minus 40 divided by 3 minus 0, because that's actually my slope formula. Y2 minus Y1 over X2 minus X1. And actually, those are really easy numbers to work with. 65 minus 14 is 25. 3 minus 0 is 3. So 25 divided by 3. And that slope is roughly, what's exactly 25 over 3? It's like 8.33. So, okay, there's my slope. 8.33 hours, H. And what's my starting point? Well, my starting point is the y-intercept. What's the y-intercept in this problem? 40. There you go. I just built my equation. Awesome. 3. Now the real number 3, not the number 4 I just did. According to your line of best fit, how many hours would you expect to study in order to earn a semester grade of 100%? Well, when I look at this, I can just follow my line. Where does it hit 100? Right there. Boom. Looks like 7 hours. Awesome. A couple more questions on the next page. Explain what the slope of the line of best fit represents in the scatter plot above. Oh, for every additional hour I study, I'm going to get an extra 8 1/3, 25 over 3 percentage points on my semester grade. Right? Discuss what kinds of data sets might have a linear relationship and would be interesting to make predictions for. I'm really curious about like things involving effort and working out, practice and performance, maybe things with heat, melting. And actually, you're going to explore these topics much more yourself. Hey, I hope this video didn't go too long and was helpful and meaningful. You got an example of here how to answer these questions, and this should help you with your book work and your projects.